Question 6.2 asks to find the heat transfer coefficients. We assume steady operating conditions. Edge effects are negligible. We know our velocity, our area, our friction coefficient. We know the air is at negative 50 degrees Celsius, so we grab our properties from table A15. We solve for the density using the ideal gas. We plug that back into the equation for the heat transfer coefficient, and we solve for the heat transfer coefficient. Question 7.28, it's asked to find the minimum free stream velocity the fans need to supply to avoid overheating and to avoid the overheating. We assume the fins and base plate are nearly isothermal. Radiation heat transfer is negligible. Laminar over entire fin surface of the transformer. So we have our knowns, and we have the T infinity and T surface. We solve for the bulk temperature. We grab our properties, table A15. Solve for finned area, unfinned area, total area. Then we solve for Q. Then we solve for the Nusselt number. And then solving for the Reynolds number, and then we finally solve for the Reynolds number. We rearrange the Reynolds number to solve for the velocity. Question 891 wants us to find the length and the temperature of the surface. We assume steady operating conditions. Thermal resistance in tube is negligible. Inner surface of the tube are smooth. We have our knowns, and we solve for the bulk temperature, and we grab our properties from table A15 again. And here it says that a Q is 350 BTU hour per foot, which is going to help us solve for the length. So the length is Q total over Q. The energy units cancel out, and we have feet left. Then we solve for the Reynolds number using the velocity. Then we solve for the Nusselt number, and then we solve for the heat transfer coefficient, which helps us solve for the flux, and we rearrange that equation to get the temperature of the surface. Question 9.143 asks us to find the fraction of heat loss from the outer surfaces of the electronic box. We assume steady operating conditions. Air is an ideal gas with constant property. Heat transfer from the base surface is negligible. Pressure of air in enclosure is 1 atm. Again, we solve for bulk temperature and grab our properties from table A15. We solve for the volume expansion coefficient, and then the Rydberg we use the Rydberg formula and then solve for the Nusselt number. Then we solve for the Q of the top, since that's an exposed surface. Then we repeat the same process, and we solve Q from the sides. Then that allows us to solve for the friction factor, which is 16%. Last question, 1066. We need to find local H at the middle and bottom of the plate. We assume steady operating condition. Plate surface has uniform temperature. The flow is laminar. We again grab our properties, but this time from table A2, since it is liquid, and table A9. From table A2, we grab the modified latent heat vaporization, and then we solve for the modified latent heat vaporization here, and then we solve for the Reynolds number, and we see that it is less than 1,800, so our flow is laminar, and our assumption is correct. I was very confused on this question. There were many formulas, VHX, which I was very confused about. I tried reading, but I was still a little confused when it came to these formulas. I was also a little bit confused when to use all of the different versions of the Reynolds number equations and the Nusselt number equations that were given to us.